Okay, so this is activity 216, step-by-step truss system. You're going to need a straight edge, probably a calculator and a pencil. And this is the truss that you will be stepping through. I have a 1,000 pound force, a 500 pound force, a 250 pound force, and this truss is supported by a pinned connection here and a roller connection here. It is 3 units tall. From A to D it is 3 units. From D to point B here it is 2 units. From B to E it is 2 units. And from E to C it is 3 units. The entire length of the truss is 3 plus 2 plus 2 plus 3, which is a total of 10 units. So if you flip the page here, number 1 says draw a free body diagram for the entire truss structure illustrated above or on the opposite page. Make sure to include all known and unknown angles, forces, and distances. Calculate and determine all angles using trigonometry and geometry. So it says 1 box is equal to 0.5 units. And what they have done here is they have made this box pretty much exactly the size that it needs to be for you to get this to fit in here appropriately. So what you're going to do is you're going to start in this lower left hand corner here. It is 3 units tall, but they're telling you that 1 box is equal to 0.5 units. So you're going to go up 6 boxes. From that point on the truss to point D up here, we go up 6 and over 6. So 1, 2, 3, 4, 5, 6. That is going to be point D. From there to point E is 4 units, which will be 8 boxes. So 1, 2, 3, 4. That's kind of the midpoint there. 5, 6, 7, 8. This will be point E. Point B is halfway in between D and E, and it will be here. Actually, let me write that off to the side because we're going to need to draw the force in there. This is point B. And point C is 6 units and then down 6 units, so it will be there. Then you want to use your straight edge. This is point A. You use your straight edge to draw in the members of your truss. Then we want to mark any known angles. Since this is 3 units and 3 units, we know that this angle here is 45 degrees because it's a 45, 45, 90 triangle where the legs are the same. We also know that this angle over here is also 45. If we look at this angle here, then that's going to be 6 units for the opposite side and 4 units for the adjacent side. So if I say inverse tangent of 6 over 4, that will give me that this angle here is 56.31 degrees. If I do the same thing for this angle here, it's going to be 6 units over 4 units as well, so this angle is 56.310 degrees. If I put my dimensioning lines in, this is 3. That's 3 as well. 3 units there, and 3 there. At point D, we have a 1,000 pound force at point E, we have a 500 pound force. And at point B, we have a 250 pound force. On point A here, we have a pinned connection, so that means we're going to have 2 supporting forces. It's going to be R, A, Y. And R, A, X. Point C here is a roller. So that means that we just have the 1 vertical supporting reaction force. We'll call that RCY. Again, the R just stands for the reaction at C in the Y direction, the reaction at A in the X direction, reaction at A in the Y direction. That's what those subscripts stand for. Number 2, calculate reaction forces at the roller and pin connections. Part A, list static equilibrium equations. Hint, they all involve summations. So we're going to say the sum of the forces in the X direction equals 0. The sum of the forces in the Y direction equals 0. And the sum of the moments equals 0. It's also a good point just to check, but I mean I wouldn't have you doing it if it wasn't true, that we can actually solve this. So 2J is equal to M plus R. We have 1, 2, 3, 4, 5 joints, so that's going to be 2 times 5. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 members. And 3 reaction forces. So that gives us 10 equals 10. So we can actually solve this truss. B. List all known and unknown forces acting and reacting on the truss structure. Label direction of force with an arrow. So forces in the X direction, the only one that I have is RAX. In the y direction, I have, and RAX is to the right. In the y direction, I have RAY, which is upward. I have the RCY, which is upward. I have a 1,000 pound force at point D, which is downward. Have a 500 pound force at point E, which is again downward. And a 250 pound force at point B, which is downward as well. The next thing to do is to look at the moments. So moment forces determined from pin A. Pin A is going to be where it would rotate if we let it. So my moments, not including point A, I have a 1,000 pound force. That is 3 units away. The 1,000 pound force is downward, so I make it negative. And that gives me a moment of negative 3,000. And let's say that our units are in feet. Would be foot-pounds for that moment. I have a negative 250 pound force. That is 5 units or 5 feet away. So that's going to give me negative 1,250 foot-pounds. The 500 pound force is 7 feet away. So that's minus 3,500 foot-pounds. RCY is an unknown force, but it is positive, and that is 10 units or 10 feet away. So that's just going to be 10 times RCY. I'm going to use that information on part C. That information on part C. Part C says use the moment static equilibrium equation acting upon pin A to solve for RCY. So my equation is the sum of the moments equals 0. So I'm going to have negative 3,000 plus negative 1,250 plus negative 3,500 plus 10 times RCY equals 0. Negative 3,000 plus negative 1,250 plus negative 3,500 gives me negative 7,750 plus 10 RCY equals 0. And if I move my 7,750 to the opposite side here, that gives me 10 times RCY is equal to positive 7750. I divide by 10 there. And that gives me that RCY is 775 pounds force. Now I'm going to solve for RAX and RAY. So my equation is the sum of the forces in the x direction equals 0. The only force that I have in the x direction is RAX, so that has to be equal to 0, which means that RAX is equal to 0. Solve for unknown reaction forces in the y direction. So my equation is going to be the sum of forces in the y direction equals 0. For that I have RAY plus RCY plus negative 1000 plus negative 500 plus negative 250 equals 0. These are negative here because they are pointing downward. So then I can substitute in my RCY here, which was 775. And if I add all of these together and move it to the other side, this is negative 1750. So when I move it to the other side, it becomes positive 1750. So I have RAY plus 775 is equal to 1750. I subtract 775. And that gives me that RAY is 975 pounds force. And if you get to that point, the rest of it is just using the trig to find the forces along each of the beams. So we have found the moments, we found the reaction forces, and now, just like in our notes, we have to go and solve for the force along each member. We have to determine whether they are in tension or whether or not they are in compression. So flip the page here. You have really technically already done this. All you need to do here is go back and annotate with the numbers for RAX, RAY, and RCY. So number 3 here, we put point or joint A here. Again, we're not going to worry about RAX because it's 0. So we're going to draw RAY here. RAY is 975 pounds. Again, we're going to assume that AD, which is the beam or the member that goes up at the angle here of 45 degrees, we're going to assume that that is under tension. So we go up 6 and over 6. 6, 1, 2, 3, 4, 5, 6. We're going to assume that that force is under tension, so it will be drawn back towards A like that. So that is force AB. I'm sorry, AD. AD. B is down here. This is AD, not AB. D is 2 boxes away, or 4 boxes away, so point D is actually right there. And we are going to assume that that one is in tension as well. So it'll go back towards point A as such. So, part B, use SOHCAHTOA, that's your trig stuff, to express ADX and ADY in terms of AD. So, I'm going to have sine cosine of theta, with the theta being the 45 degrees here, equal to the adjacent side divided by the hypotenuse. So that's going to be cosine of 45 is equal to ADX divided by AD, and that means that ADX is going to be AD times the cosine of 45. ADY, I'm going to say sine of theta is equal to opposite over hypotenuse. So that's going to be sine of 45 is equal to ADY divided by AD. And that means that ADY is AD sine of 45. Okay, so my forces in the x direction, I have RAX, which is 0. I have AB, which is positive because I'm showing it pointing to the right. And I have ADX, which is AD cosine of 45, and I'm showing that as pointing to the left, so that's going to be negative. In the y direction, I have RAY, which is 975 pounds. And I have ADY, which is AD sine of 45. Part D. Use static equilibrium equations to solve for AD and AB. Solve for AD by calculating the y direction static equilibrium. So your equation, sum of the forces in the y direction equals 0. So 975, that's RAY, plus ADY, which is AD sine of 45. So that means that, equals 0. AD sine of 45 equals negative 975 pounds. So I divide by sine of 45, and that gives me AD is negative 975 divided by sine of 45, and that means that AD is negative 1378.86 pounds force. And that means that it is under compression. Solve for AB by so we flip the arrow here. Okay, we flip the arrow here. Now we're going to solve for AB by calculating the x direction of static equilibrium. So I'm going to say the sum of the forces in the x direction equals 0. So I have 0 for RAX, and then minus AB because I'm showing it under tension, so it should be pointing to the left, and then plus so plus AB there because I have it under tension and it's pointing in the positive x direction. Plus my AD cosine 45.